Everyone, welcome to the continuing videos in the linear algebra series. So in this video, as you can see on the screen, we're going to be talking about the properties of the determinant. So we've already seen in previous videos at least one method in terms of how to compute the determinant, including some row reduction techniques, or because one of the properties that we've seen, which is the determinant of the transpose, is the same. Anything we can do with a row, we can do with a column as well. So what we're going to see in this video is some other properties of the determinant, as well as wrapping it up with some of the properties that we would have already seen, involving a variety of other topics that's already been explored in our linear algebra. So there's one main application or property we're going to be seeing here. That being said, there are a couple little ones that we've already talked about in terms of relating it back to row reductions and matrices, elementary matrices, stuff like that. So let's just recall one of the properties we saw with row reduction, that if A becomes B by multiplying row I, technically column as well, but we'll stick with row I, by K, then the determinant of B is equal to K times the determinant of A. That was just one of our properties you would have seen, how to relate it to row reduction, etc. Of course, that could naturally lead to, well, then, could we get a formula for this? So what is the determinant of K times A? Again, feel free to pause the video and think about this in terms of getting an answer. Alright, so perhaps the most natural thought might be, well, then it's just K times the determinant of A. But that doesn't really match with what we just said in the line above. We get that property if we just multiply one row by K. Not the entire matrix, but just one row. So if we want to multiply the entire matrix by K, then we're multiplying every row by A. In other words, the real property is K to the power of N, and the N is the number of rows in the matrix. Of course, for determinant, we need square matrices, and so we have an n by n square matrix. So if we double the matrix, if we go 2 times A, that doesn't mean we're doubling the determinant. We could be multiplying the determinant by 8 if it's a 3 by 3 matrix, or 32 if it's a 5 by 5 matrix. We multiply by 2 for every single row, equivalently every single column. So this is one property we have here that can actually deal with multiplying things in general. That being said, we're going to look at this property a little bit more and think back to something we saw with elementary matrices back in a previous video. Namely, if E is the elementary matrix corresponding to the above property, so for row I becomes K times row I, my question to you is, what is the determinant of E? What is our determinant of E? Well, there's two ways we can think about this. The first way we can think about this is we could just do it directly. You're going to end up getting a 1, 1, 1, a K somewhere, and then 1. That's going to be our elementary matrix, and then we could just use our rule for determinants of elementary matrices. Equivalently, we could also use the property and say, well, it would be the identity, which has a determinant 1, times K. Either way, we get that this is K. And similarly, for swapping two rows, the determinant of that elementary matrix would be -1. And if we take row I, that's row I plus a multiple of another row, the determinant of E is equal to 1. So we can verify these things directly. For example, this last one, assuming row J is underneath it somewhere, we're going to get 1s all the way down the diagonal, and then just a random K either up there in the upper triangle or in the lower triangle. But not both. Everything else is going to be 0, which means it's triangular. We just multiply along the diagonal. And so we get these right here. In other words, the determinant of the elementary matrix is going to be the same as what we would get for the row operation. So, in other words, the determinant of an elementary matrix times B is equal to the determinant of an elementary matrix times the determinant of B, which seems to lead to an interesting property about determinants in matrix multiplication. Namely, it appears, at least for elementary matrices, that the multiplication can be split up. Of course, not every matrix is an elementary matrix. However, what we do know from some earlier stuff that we would have seen is that if A is invertible, then A is the product of elementary matrices. And so the determinant of A times B is going to be the determinant of all of these things multiplied together times B. And now we can use the elementary matrix rule over and over and over again and then we can slam these ones back together. Of course, that's a big if to say if the matrix is invertible, but certainly get this right here. So a question you might want to ask yourself is, what if the matrix is not invertible? Is this still true? So would this still be true if the matrix is not invertible? And by this, I mean this property right here about multiplication. So, the answer to this is, well, what happens if it isn't? What happens if our matrix is not going to be invertible? What happens then? And the idea here is, well, if it's not invertible, we know that when we row reduce it, its reduced row echelon form has a row of zeros. So if A is not invertible, then A is equal to a bunch of elementary matrices times a reduced row echelon form that has a row of zeros. And thus the same rule would say that the determinant of A is equal to all of these determinants but if the determinant of R has a row of zeros, again, feel free to pause the video to remind yourself, what is the determinant of R? Well, that would just be 0. So if A is not invertible, then the determinant Well, the determinant is going to be 0. If A is invertible, we know the determinant is non-zero, which leads to its own property on its own. But in terms of this one right here, AB is also not invertible. And hence, the determinant of AB, they're both equal to 0. So technically the property still works. If AB, or if A is not invertible, then AB is also not invertible. So they're equal to each other because they're both equal to 0 for the exact same reason. So there we go. And so we have this property and this one more rule that we can wrap up into our list of equivalent statements. Namely, the ones we already had. If A is n by n, A is invertible. AX equals 0 has only the trivial solution. The reduced row echelon form of A is I, technically the n by n identity matrix. Just kind of wrapped up in what we've already seen. A is a product, as we saw above, of elementary matrices. AX equals B is consistent. For all n by 1 vectors B. And has only exactly one solution. So all of these ones that we had from before now we can add in the last one to deal with the determinant. So again, feel free to pause the video and fill in that blank. That's right. The determinant of A is non-zero. So if we remember where all this started, this whole thing started with that 1 over AD minus BC for the inverse of a 2 by 2 matrix, where we knew a 2 by 2 matrix was invertible if and only if this denominator was 0. So we've defined the determinant that performs a very similar calculation. Unfortunately, at least right now, there's no exact equivalence to this. Granted, there will be kind of one eventually. But at least we have the same property of when the inverse exists. So a determinant calculation can tell you when the inverse exists, and hence whether or not there's a point of going through the row reduction process. Okay. There's one more property to take a look at, and I'll leave this up to you, is what is the determinant of A inverse, assuming that it's invertible. Assuming that we're not, that A inverse even exists, aka the determinant of A is non-zero, what would that inverse be? Hope you had a chance to pause the video. The property we can use is that A times A inverse is I, and take the determinant of both sides, noting now that we can split these two up. namely the determinant of A times the determinant of A inverse, is equal to the determinant of I, and we know the determinant of I. So this is 1 over the determinant of A. Of course, the determinant has to be non-zero, but it had to be non-zero for the inverse to exist anyway. There we go. And we have a bunch of properties about multiplying matrices by things, multiplying matrices by each other, even finding inverses. Anyway, so that's it for these videos. Just a list of a bunch of these properties that can be used in order to find the determinants of matrices if we're combining together other things. But one quick little note, while we did it for multiplication, and if you want to think of inverses being close to division, kind of did it for that as well, but there's no property for addition and subtraction, at least no nice property. It's certainly not true that the determinant of A plus B is the determinant of A plus the determinant of B. That just is not a true statement. Addition or multiplication and inverse is fine. Addition and subtraction, unfortunately, don't work. It's kind of like logarithms. You got properties for multiplying and dividing, but not for addition and subtraction. So that's it for a list of videos, and probably in a future video we'll see some of these in action in terms of, relating back to some other topics.